Hello everyone and welcome again to CSEN701 Embedded Systems Architecture, also referred to as Real-Time Embedded Systems. Today we are going to discuss Tutorial 5 Part 2, which actually marks the beginning of the second chapter in our course, which is the Real-Time Operating Systems chapter. As you all know, the content of this video will not be given on campus, so you need to watch it online. We only gave part 1 of tutorial 5 on campus. However, part 2 of tutorial 5, which is this video, will be given exclusively online. So now let's start with our content. As I stated in the previous video, which was tutorial 5 part 1, the analog to digital converter marked the end of our microcontrollers chapter. And now we are going to introduce a new chapter or a new concept called the real-time operating systems concept, and we are going to do some practical work with one of its applications, which is FreeRTOS. Before actually introducing real-time operating systems, don't worry, we are going to refer to some operating system concepts which you took in semester 6 in the OS course. However, any concept we are going to explain, we are going to explain it from the beginning, as if you do not know what it is, because not all of you took the OS course. So it's not actually fair to continue on the knowledge you have. We'll just mention some of the stuff stated in the OS course. However, important concepts will be recapped from the beginning, so everyone will be refreshed with these concepts. So let's start with a quick recap regarding what is a real-time operating system. A real-time operating system, which is also referred as RTOS, is an operating system that guarantees a certain capability within a specified time constraint. So actually the main difference between real-time operating systems and the normal operating systems that you have on your desktop PCs or laptops is that real-time operating systems have some time constraints, okay? They actually try to make all tasks running meet their deadlines. As I told you before, when we were explaining what are real-time embedded systems had some time constraints that must be met. Real-time operating systems also have these constraints regarding the tasks that are running inside the device, and actually real-time operating systems are mainly used for embedded systems. So if I want to turn a normal embedded system into a real-time embedded system, I need to flash a real-time operating system on it to make sure that all the tasks inside this embedded system or microcontroller will meet their specified deadline. And that's why the second chapter in our course is the real-time operating systems, because we actually talked about embedded systems and real-time embedded systems. Then how can we turn an embedded system into a real-time embedded system? By actually using a real-time operating system that makes sure that all the tasks in the embedded system will meet their specified deadlines. So, as you all know, operating systems have different functionalities to perform, and a real-time operating system has four main functionalities. The first functionality is the task management, which is related to the tasks creation and deletion, controlling tasks, scheduling, and finally obtaining tasks information. So actually, as you can see from this figure, the task management is related to actually keeping track where is the task, is in which state, and actually it is responsible for creating such tasks, deleting such tasks, and obtaining the tasks information. The second functionality is the scheduling. So actually we need to have a scheduling algorithm, and a real-time operating system chooses a scheduling algorithm, or the developer may actually predefine a certain scheduling algorithm to be performed. And in real-time operating systems, we focus on scheduling algorithms that make sure that all of our tasks meet their deadlines, because we're in a real-time system, we're in a real-time operating system, and actually we are time bounded. So we need to make sure that all of our tasks in the system meet their deadlines. They should not actually miss any of their deadlines, or if they have some tolerance, they can miss. However, our main goal is that all of our tasks must meet their deadline. Therefore, a real-time operating system makes sure to select the most suitable scheduling algorithm as you took from the OS course, you took multiple scheduling algorithms, and here in the embedded systems course, we'll be taking 2 additional scheduling algorithms that are related to time, okay? And as you all know, a scheduling algorithm is used to select or choose which task to be in the running state or which task will execute in a particular time. So actually the order of execution of tasks is maintained by or determined by the scheduling algorithm, and a real-time operating system is implementing the policy of this particular scheduling algorithm. The third functionality is the resource allocation. Actually, tasks which are single user threaded processes, but in embedded systems, actually may need some resources, like for example, space in the memory, want to access some files, want to access some IO devices. So a real-time operating system will try to manage the resource allocation to tasks and to prevent deadlocks. Finally, the fourth function is the interrupt handling, and a real-time operating system must cope and know how to handle an interrupt when it occurs. So actually an interrupt may occur, a real-time operating system must know how to handle such interrupt and then continue the execution of the program or the rest of the tasks normally. So four main functionalities: task management, scheduling, resource allocation, and interrupt handling. And as you can see here, we have the different states a task can be present in. And these states are actually maintained by the task management function or functionality in a real-time operating system. At the beginning, when I start actually running my microcontroller, which has a real-time embedded, a real-time operating system on it, or in general, if I'm actually running a real-time operating system, the first state will be the non-existing state. So I did not yet create any tasks. I did not execute the create task function. Okay, so when I'm actually programming, I will be calling the create task function to create my different tasks. In the non-existing state, I have 0 tasks. Okay, so when I start executing the create task or the task create function, it will create a task and move it to the ready state. So when I create a task, when I execute the line of the task creation function, or when I call the task create function, it will create a task and put this task in the ready state. Putting it in the ready state means it can be selected by the scheduling algorithm at any time. It is ready to run at any time. However, you can actually delete this task. And to delete this task, the task must be in the ready state, and then I can destroy or delete it, and therefore this task will no longer be available and it will be in the non-existing state. So in the non-existing state, if I create a task, it will be created and it will move to the ready state. If I destroy or delete a task, it will return back to the non-existing state. Now let's assume we have a task in the ready state, and when a scheduling algorithm or when the scheduler, which is responsible for implementing the scheduling algorithm, selects or elects this particular task to run, it will move to the running state. So as you can see from the ready state, it will be elected and it will move to the running state. However, if this task finishes execution, it will return back to the ready state. So actually this task has some code to perform. It performed this code, it finished, it will return back to the ready state. However, there is another scenario where a task can move from the running state to the ready state, which is the preemption state. So if I'm a task in the running state, however, the scheduler decided to run a different task, this task will be preempted. The task in the running state will be preempted and it will return back to the ready state, and then the task that the scheduler chose to run instead of the running task will move to the running state, because I cannot have more than one task in the running state. So actually in the real-time operating system or in the free RTOS, which we'll be talking about or we will be using for our practical examples, we can only have one running task. I cannot have more than one task running. Okay, we're a single threaded user processes. So actually if I'm in the running state, so let's talk about a different scenario. If I am in the running state, however, I am waiting for an I/O device, or actually I want, for example, to access the printer, but the printer is occupied. So what will happen? It will be blocked, okay? So it will be blocked, meaning that it will move to the waiting state. Moving to the waiting state means it did not finish its execution. However, and by the way, it was not preempted by another task. It has the highest priority for now. However, it is waiting for a certain resource that is not actually available, like an I/O resource, or it decided, for example, to be in a delay state for 1 second or 2 seconds. So there are two types that makes a task move to the waiting state. Either it is waiting to access a resource and this resource is not available, so it needs to wait for this resource to be available, or actually this task is implementing some sort of delays and it needs to sleep, for example, for 1 or 2 seconds, then wake up again. Therefore, it will move to the waiting state. Moving to the waiting state does not mean that it finished execution, and it does not mean that another task preempted this task. No, still, the scheduler wants this task to finish execution. However, it is waiting for a resource that is not available, or this task itself has some delay inside it and it needs to sleep for a period of time. Therefore, it will move to the waiting state. And when it moves to the waiting state, the scheduler will choose the second highest priority task to run according to the scheduling algorithm. Okay? So while task X, which actually the scheduler chose, went to the waiting state because it is waiting for an I/O device to access and it is not available yet. So the scheduler will see the second task that can run while the task X is waiting in the waiting state. And then, for example, task Y will be selected by the scheduler and will move to the running state. And then, when, for example, the printer or the resource I was looking or I was waiting for finishes and is available to be used by task X, task X will move from the waiting state to the ready state, which means the printer is available. And when it moves back to the ready state, the scheduler will see that task X has, for example, a higher priority than task Y, which is actually running. So it will preempt task Y and will allow task X to run and continue running back. So let's just have this simple scenario. As I told you, the scheduler, we have two tasks, X and Y. The scheduler chose task X to run. It is the time for task X to run. So it moved from the ready state to the running state. Okay? Then, while it was running, task X requested the use of a certain I/O device, for example, the printer. However, the printer is not available. Okay, it is actually used, it is blocked by a certain task, or actually that it is not connected. It wants to access the printer and the printer is not available for any reason. Okay, so it will move from the running state to the waiting state. Once it moves to the waiting state, the scheduler will choose another task, which in our system will be task Y, to run, because at least I must have one task in the running state. I cannot have 0 tasks in the running state. In a real-time operating system, I must have at least one task in the running state, or I must have a task in the running state in general, depending on the real-time operating system. Okay, so here task Y is running and task X is in the waiting state. However, the printer became available. This I/O device became available. Therefore, task X will move from the waiting state to the ready state. Once it is in the ready state, the scheduler will see that task X had a higher priority than the running task, which is task Y in the running state. So it will kick task Y from the running state and it will move back to the ready state, and then task X will be chosen again to run, and it will move to the running state and it will use the printer or the I/O device it was waiting for and will continue executing. So as you can see, I can move from running to waiting, but I cannot move from waiting to running. I need to go back to the ready state. It is very important. Okay? This just describes in general the concept or the general states we have that a task can be present in, and the flow of a task in this state diagram. However, it depends on the real-time operating system, on, for example, the number of tasks that can be running in parallel, or, for example, in our case, we can only have one task running. So if another task wants to run, it needs to actually kick the running task if it has a higher priority than the running task. And a rule of thumb for all types of real-time operating systems, I must have one task in the running state, whether it is the maximum or I can have multiple tasks, but I mean, I need to have at least one task in the running state. I cannot have 0 tasks in the running state. And we'll see how our system, the FreeRTOS system, when we use it in our practical work, makes sure that we have at least one task in the running state. Now let's move on to our question. This exercise presents a Windows port layer for FreeRTOS that has been developed and tested using Visual Studio Community Edition with the Ming WGCC based compiler. So actually we'll be using a real-time operating system which is called FreeRTOS, and it's an open source free real-time operating system, I mean. And this operating system, we can actually simulate it on Visual Studio. So if you have Visual Studio, you can actually run FreeRTOS. By the way, it can also be run on microcontrollers because its main functionality or main role or main purpose is to run on embedded systems or microcontrollers. So FreeRTOS is compatible with the Arduino boards. However, just for simulation, we want to simulate, we'll be using Visual Studio and we'll be using Windows. So if you're a Linux or Mac OS, this will not work. However, if you're a Windows user, you can actually try the Visual Studio FreeRTOS edition. Moving on, the Windows port layer creates a low priority Windows thread for each FreeRTOS task created by the FreeRTOS application. So this is just an explanation or a description of how does Windows simulate FreeRTOS, or actually how are we simulating a real-time operating system on Windows using the FreeRTOS application. To open FreeRTOS on Windows using Visual Studio, you need to follow these steps. We'll be providing you with a zip file, and you will actually follow these steps in order to run FreeRTOS using Visual Studio on your Windows machine. So you'll open FreeRTOS, then this will be the zip file name. Then you'll find a folder called FreeRTOS, another folder called demo. Then we have Win32-MSVC, and then finally we'll have Win32. Although I'm working on a Mac device, but I can actually show you this sequence. So if we actually just see our folder, this will be our folder. We'll double click on it. Then we'll be selecting FreeRTOS. Then we'll be selecting demo. Then we'll be selecting Win32-MSVC. And this one, you need to open the Win32.solution file. It will open then Visual Studio, and you will follow the next steps. So if we go back to our slides, the next step will be that when you open the Win32.solution document or solution file, I mean, you'll find out that Visual Studio will open, and on the right, you will find the Solution Explorer. Okay, so you'll actually choose Demo App Source, then you will choose Blinky_demo, and then you will choose main_blinky.c. And take care, all of our code will be written inside the main_blinky.c. We'll not write any code outside of it. You cannot create files, okay? If you want to actually create a new file, you need to edit the main_blinky.c. Because this is a template, a ready-made template, and you edit inside the template. You cannot create new files. It will not work, okay? And all of this will be available in the Solution Explorer, which will be available on the right of the screen when you open the Win32.solution file. So for the next upcoming questions, we'll be using the FreeRTOS Windows simulation. And by the way, FreeRTOS implements a scheduling mechanism based on priorities. So actually, the developer will assign priorities to tasks, and according to the priority, the scheduler will choose this task to run. And from here, this will be different than the two scheduling algorithms you will be taking in class. So in class, we'll be taking the rate monotonic, the RM, and the EDF, earliest deadline first. These two scheduling algorithms are not actually implemented in FreeRTOS. So FreeRTOS implements a third paradigm, which is a priority-based paradigm, meaning that the programmer will assign priorities to tasks, and when a task with a higher priority is available in the ready state, the scheduler will automatically choose it. However, if all tasks have the same priority, a concept of time slicing or the time slicing mechanism will occur, meaning that it will distribute time equally to all the tasks. So if the priorities are not equal, we have different priorities, the higher priority tasks will be running. However, if all priorities are equal, the scheduler will perform a time slicing operation, meaning that it will dedicate the same exact amount of time to each task. So for example, task 1 will run for 5 seconds, task 2 will run for 5 seconds, then task 1 will run for another 5 seconds, then task 2 will run for another 5 seconds, and so on. In this scenario will only occur if all tasks have the same priority. However, if there are different priorities, the largest priority task will be elected or will be selected until it sleeps or it has some internal delay, so other tasks can run. Because actually, if I have three tasks with three different priorities, and the highest priority task does not sleep, what will happen? It will always run. It will be a continuous task. However, if I want to create periodic tasks, meaning that they sleep and wake, assigning different priorities makes sense now, because when the highest priority task is sleeping, the next highest priority task will be the one running, and so on. So to sum up this part, in FreeRTOS, it is a priority-based scheduling algorithm or mechanism, meaning that the highest priority given to a task or a task with the highest priority will always run. However, if all tasks have the same priority, then time slicing will occur or will happen, meaning that all tasks will be given the same amount of time to run. Okay? And as the example I told you, 5 seconds, then 5 seconds, or for example, 3 seconds or 3 seconds, you do not know how the scheduler will actually divide time upon the tasks, but we know for sure that each task will run for the same amount of time if they all have the same priority. And when I mean if they all have, I mean all the tasks in the ready state have the same priority. Okay? So now let's move on and actually how to create a task in FreeRTOS. We have here a function called the xTaskCreate, which actually takes 6 parameters. So the xTaskCreate is responsible for creating tasks, and you as a programmer, you will create tasks by calling the taskCreate function with the 6 different parameters. And take care, xTaskCreate is used to initialize tasks, okay? It is just used to include the task in the scheduling options. But actually, to create or to implement a task, you create a simple function or method in your code. So it's like Java when you create multiple methods in your code. A task is actually a function or a method. However, it is just in the air, okay? If you want to include this function or this method in the scheduling options, you need to initialize it with xTaskCreate. But however, in general, a task is normally implemented as a function or a method, and then its body contains the code that you want to execute. This task that I wrote, or this method that I wrote, now I want to actually include it in the scheduling option. I want the scheduler to actually put it in the ready state and select it at a certain point of time. So I need to initialize it with the xTaskCreate. However, I do not create the actual task using xTaskCreate. No, xTaskCreate is a function that just includes the already created function or method to the scheduler options. Okay, so let's start with the first parameter, which is the task code. This is the first parameter. Pointer to the task entry function, just the name of the function that implements the task. So actually, as I told you, tasks are implemented as functions or methods. In order to initialize and to actually include it in the scheduler options, I call xTaskCreate, and the first parameter will be the name of the function that you already created. So for example, if I created a function or a method called addition, Then the first parameter will be its name, which is addition, which will notify the scheduler that this addition function is a task. It's just not a helper function or a helper method. No, it's a task and I want to schedule it. Okay? Tasks are normally implemented as an infinite loop and must never attempt to return or exit from their implementing function. Tasks can, however, delete themselves. So actually, since we are working in a real-time embedded system and a real-time operating system, we need to have tasks running in an infinite loop because what? They must be real-time. Real-time, for example, means they must operate 24/7. They must sense the environment 24/7. So I cannot have a real-time task that just executes once in the entire code or the entire time. So all tasks, you will see that a while one is implemented inside the body of all tasks because they are real-time tasks. And since we are dealing with real-time, you will always see infinite loops because they will be working 24/7. They will not stop. They will be working forever. Therefore, tasks, when you create, for example, the addition function or the addition method, inside the body of it, you will find a while one, and the code that I want to execute will be inside this while one. Therefore, a rule of thumb, tasks will always be implemented using infinite loops. So inside the task, you must have an infinite loop just to make sure that it is a real-time task. Okay, so here the first parameter will be the task name, or actually the name of the function that you already implemented and you want to make it a task. And we'll be seeing example at the end after I finish describing all of these parameters. We'll be finding examples on actually how to initialize tasks. Okay, the second parameter is the PC name, a descriptive name for the task. This is mainly used to facilitate debugging, but can also be used to obtain a task handle. So mainly, if the first parameter was the actual name of the function or method implemented in the code, the second parameter is just a human name given by the programmer for this task, and it could be anything. Okay, so for example, the function is already implemented called addition. So the first parameter was called addition because the function name is addition. The function that I want to turn into a task is called addition. Therefore, the first parameter is the actual physical task name present inside the code. However, the second parameter is just any name you want to give it. So for example, you can call it add, you can call it summation, you can call it anything. It is just a human name you give it to this task, because if the task name is not actually descriptive, for example, if the task was not called addition, the function that you implemented was not called addition, it was called task1. So the first parameter will be task1. However, as a programmer, for debugging purposes, you need to know what is the role of task1. So you may give it a human name in the second parameter. So you can call it in the second parameter summation. However, the actual implemented task inside the code is called task1, but you wanted to give it a human name for debugging purposes. Okay, so the difference between the first parameter and the second parameter, the first parameter is the actual name of the function or method present in the code. The second parameter is just an imaginary name you give it to describe this function or method. Okay, now the third parameter is the stack depth. Definitely you will find weird stuff like, for example, here US stack depth and here PV task code. Actually, these are some terminologies being used inside the free RTOS system. Like here, for example, X task create. Okay, it is just some sort of a convention, and we just want to understand the name. So it's called stack depth, for example, or task code. And in the exam, you should not actually 100% know the syntax when you write code. Okay, if you say task create instead of X task create, we will pass it. It's not a programming course at the end. So now let's see what is the role of the third parameter, which is stack depth. The number of words, not bytes, to allocate for use as the task's stack. So actually for each task you try to implement, you need to allocate some sort of space, okay, from the memory. So any internal calculation occurring inside this task will use the allocated space, and it cannot use more than the allocated space. So take care, because you may actually sign a small amount of space or small memory space to a certain task, but it needs a larger space, therefore it will not perform its correct functionality. So take care, because you will face this problem in the project when you assign tasks, when you assign space depths or stack depths for a certain task, and actually the task is performing, but it is not actually performing the correct function it should do, or it should perform, because there are the space is too little or too small for it. So actually you need to increase the size that you allocate for this task. So actually each task can only operate within the specified amount or the specified number of words you allocate to this task. It cannot exceed the number of words that you allocate for this task, or it cannot exceed the space you allocated for this task. Okay, so for example, if you assign 100 words, it cannot actually work outside of the 100 words. It will try to actually fit in the 100 words, and if it could not fit, it will not perform the correct functionality. So this is actually one of the best options in real-time operating systems, is that you allocate a certain space for each task. So actually you manage the memory in some sort as a programmer. So I want, for example, task X to only use 100 words from the memory. It should not exceed. So it provides you better management for the memory. Now let's move on to the fourth parameter, which is called parameters. Okay, a value that will be passed into the created task as the tasks parameter. So actually, I want you guys to think about the X task create as if you are calling the implemented task. So you actually implemented some functions and methods inside your code, and you want to transform them into tasks. So you will be calling on them the X task create. And instead of calling, for example, addition as it is in the main function, you will be calling it using the X task create. So actually X task create as if you are calling a certain task. And by the way, you can call a task multiple times. If I have a task that is responsible for printing, and actually it takes as an input parameter the text that it will print, this text will be provided in the fourth parameter of the X task create. So let's just assume this example. I have an implemented function called display. Okay, and actually I want to make it a task. So I will call X task create. Once you call X task create, it is as if you are calling this task, or you are calling this function. But instead of calling it display in the main function, no, I call it using the X task create. So actually I will say X task create. The first thing I will put its name, the implemented name, which is display. The second parameter is a human name, so I'm going to call it print some text. Then the stack depth, I will give it, for example, 1000 words. Then fourth, I will provide it with the text that it should print. So for example, I will say hello world, for example. So actually the text that will be taken as an input parameter to display our display function will be added in the fourth parameter of X task create. So instead of actually calling it in the main function display hello world, no, I will actually say X task create display printing some words, 1000 for the stack depth, and then hello words in a string. So actually, as I told you earlier, I want to include this task using the task create to be one of the tasks that the scheduler can choose to run. This action is called calling the task. So now, calling a task in a real-time operating system, you call tasks using the X task create. Okay, so actually if you want to call the display on two different texts, you will create what? Two tasks. One to display the first text, which is hello world, and the second, for example, to display hi embedded systems. Okay, so a function, we may have a function implemented in our code. This function can actually result in multiple tasks, like the display function. I may have implemented a display function or a display method in my code. However, I can actually create two tasks from this display function. One task that prints hello world, and the second task will create what will display, or will print hi embedded systems. And by the way, both will be given the same, for example, task code, because they both we use display function to display or print. So both tasks will have the display function as the first parameter. However, the second parameter we may call the first one printing hello world, the second one printing high embedded systems. We may assign same or different stack sizes to each one, and then the parameters variable will be different, or the parameter will be different. One will be sending hi world, hello world, and the second will be sending hi embedded systems. So, but it is also an important concept that I may have a function or a method in my code, and this function can result in multiple tasks because it takes what it has an input parameter, like the display function. Okay, I can have an input text and it prints it out. So I can create multiple tasks that actually print, but each task is printing a specific string. Okay, if PV parameters is set to the address of a variable, then the variable must still exist when the created task executes. So it is not valid to pass the address of a stack variable. It means that actually instead of sending or writing in the PV parameters hello world, for example, I may have a variable that contains the text or the string hello world. And actually you may call this variable, but the variable must exist before the X task create call. So you cannot have the variable under the X task create. You need to actually initialize it at the beginning of the code. So the parameter can actually see this value. Okay, so you can actually put directly a string or put a variable that points to a string. Both are accepted. However, you need to initialize the variable before the task create call. That's the only constraint. Okay, and I'm repeating on this concept because it is very important that you may have one function or one method in your code, but it results in multiple tasks. Okay, and actually each task is doing a different, or for example, the display task is printing a different string. So each one of them is a separate task. I can have the hello world task and the high embedded systems task. They are two separate tasks. However, what they are actually implementing the same functionality, or they are being used by the same functionality. Okay, so one function or method can result in multiple tasks through the task create function or call. That's why I told you task create. You may think of task create as if you are calling a certain function. So actually I can call the display multiple times. I can actually create multiple tasks from this display function too. Now let's move on to the fifth parameter, which is the priority. The priority at which the created task will execute. As I told you at the beginning, FreeRTOS is a priority-based scheduling real-time operating system, meaning that it actually, the programmer assigns different priorities to tasks, and the task with a higher priority will be the one chosen or elected to run or to move to the running state. So low priority numbers donate low priority tasks, meaning that the bigger the number, the higher the priority. The bigger the number you assign as the fifth parameter, which is the priority parameter, the higher the priority. The lowest priority ever we can have is 0. Therefore, if I have 3 tasks with priority 0, 1, and 2, the highest priority will be for the task with priority 2 because it has the bigger number. So the task with priority 2 will run before the task with priority 1 and before the task with priority 0. However, it will always run until this particular task with priority 2 either is destroyed or it sleeps, which means it performs some sort of delay and moves to the waiting state. When it moves to the waiting state or it is destroyed, the task with priority 1 will be elected to run next. So actually, if a task does not sleep, it will be a continuous task and it will always run. And this is the task with the highest priority, which is the biggest number assigned to priority. However, when this task sleeps or is destroyed, the next highest number will be elected to run. Finally, the sixth parameter is the created task parameter and used to pass a handle to the created task out of the xTask create function. The created task is optional and can be set to null. So actually, by the way, the fourth parameter, which is the parameters, can be set to null. I can have a void tasks. Also, the created task, which is the sixth parameter, can also be set to null. And by the way, the sixth parameter, which is the created task parameter, is used to point to this specific task. So actually, it's like a variable name it's a handle. Okay, we call it a handle, or we name it a handle, but it's like a variable name. So when you want to actually point to the created task, you point to it through this handle, because as I told you, we create tasks using the xTaskCreate function. So actually, I may have implemented some functions or methods in my code, but to transform them into tasks, we use task_create. And actually, a function or a method in my code can actually be used by multiple tasks, like the display function. I can actually create two tasks, a task printing hello world and a task printing hi embedded systems. Both are actually being implemented through the same function. However, these are two separate tasks. So how can I differentiate between the task that is printing hello world and the task that is printing hi embedded systems? And by the way, the programmer may assign different priorities to each one of them. So how can I actually point to the task that is printing hello world, or point to the task that is printing hi embedded systems, using the handle name you are going to give in the sixth parameter? So actually, the sixth parameter is the handler, or a name or a pointer that is used to point to this exact task. So actually, other tasks, when they want to access this task, they can call it using what? Using this handler name. Okay? Now we are done with the initialization of a task and how to actually create or call tasks in our system. So now let's move on to our questions. And the first question is, what are tasks? As I told you before, they can be seen as single-threaded user processes in real-time embedded systems. So actually, user processes in normal systems are called tasks in real-time embedded systems. So same concept, but different terminology. And actually, single-threaded processes contain the execution of instructions in a single sequence. In other words, one command is a process at a time. So actually, the opposite of single-threaded processes are the multi-threaded processes. These processes allow the execution of multiple parts of a program at the same time. So actually, we are dealing with single-threaded, not multi-threaded, as I told you before. So actually, you are just focusing on the execution of instructions in a single sequence. We are not just executing multiple parts of the code. A task does not actually perform multi-threading. Okay, it does not execute multiple parts of the code in its body. Now let's move on to this second question. Create two tasks that display a hello message, including their name every second. And here it says we use printf. Actually, it wants us to try it with matching priorities and then with non-matching priorities. And what do you notice? So actually, we want to create two tasks that print a hello message, and we want to give the two tasks, the first time we give them same priorities, so equal priorities, meaning that the scheduler will choose the time slicing option, dedicating the same exact amount of time for each task, and it will alternate between them after a fixed interval. However, the second time we want to test them with non-matching priorities, so actually giving a task a higher priority than the other, and this means that the task with the higher priority will be the first task to execute. However, since these are periodic tasks, not continuous tasks, meaning that they implement delays because we want to print every 1 second, therefore, both tasks will run even if we have different priorities. However, the very first time, the task with the highest priority will run first. Let's move on to the code. As you can see here, this is some simple initializations and includes for the real-time operating system, or for FreeRTOS to work. We'll be having two tasks, and we have the main underscore Blinky. The main underscore Blinky is like the main function. However, since we are using this template, the Blinky template, we are writing, or we are performing any main calls inside the main underscore Blinky. So let's first implement our tasks and then see how do we call them. Here we have our first task that we should implement. This is the code written, and I'm just going to annotate this code because in the physical tutorials on campus, we actually dealt with the code and we wrote it. So this tutorial or this video should be a revision for you if you forgot how to write, okay, or you forgot some concepts. However, you've seen this actually in the tutorial, so instead of writing it from scratch and wasting some time, we'll just try to comment the code and see what is happening here. So I want to create a task, okay? In order to create a task, I need in the beginning or at the beginning, I need to create a function or a method before actually calling it using xtask create. So we called the first task or the first function vtask1. We gave it a name vtask1, okay? And by the way, this is a signature. It takes void asterisk PV parameters in case it is going to take any parameter. Okay, so actually this is just a signature you need to know. Okay, you do not need to understand why we do this. It is just the signature of the method or the function. How to create methods or functions in FreeRTOS, this is the signature. The first thing we created is a constant string. Since we are programming in C, we do not have actually the variable string. So a string is an array of what? Of characters. Therefore, we have a pointer to the first element in the array of characters, and we gave it the name PC task name, and actually we called it task1. /n means to print in a new line, or when we print, it prints each statement in a new line. Okay, so actually we created a variable which is a string, which is an array of chars called task1, and it looks like we are going to print this variable. Then we have something weird called tick type x last wake time. So actually to implement delays, we have a function called vtask delay until and another function called vtask delay. However, there is a difference between vtask delay and vtask delay until. I'm going to tell you the difference, but let's just continue in this code and see what is happening. So here it is creating on this line, it is creating a variable of type tick type, and as an engineer in semester 7, you can deduce that tick time is measuring what? Is measuring clock ticks. So it looks like it's a data type that actually stores clock ticks. And we gave a name to this variable last wake time. And then we say last wake time is equal to task get tick count. So it is actually like, for example, getting the timestamp. However, instead of getting it in our normal time format, it will return it or retrieve it in clock ticks. Okay, so it is actually will inform me how many clock ticks have passed since the beginning of the code. Okay, so it's like what? Retrieving a timestamp. For example, it will tell me you are in clock tick 5. Okay, so 5 clock ticks have passed. It is just retrieving the current clock tick I am in, okay, or I'm starting to begin with. So you should only know that it retrieves clock ticks and it is like a timestamp. I want to know I am in which clock tick, okay, or how many clock ticks have passed since the beginning of executing this program. Then we will have our lovely while one. As I told you before, all tasks should be implemented in an infinite loop. So actually, at the before the while one, we had some initializations. However, the main body is inside the while one, which is the infinite loop. And here I'm printing hello from, followed by the task name. So I'm having two print statements. The first one I'm printing hello from, then the task name, which will be in this case task one. Finally, I'm performing here vtask delay until, and vtask delay until takes two parameters. It takes a reference clock tick, and it takes how many clock ticks do you want to sleep from this particular reference you specified in the first parameter. And this is the main difference between vtask delay until and the other one, which is vtask delay. So actually, in a normal vtask delay, 2 ticks. This is a normal vtask delay, okay, and above it is the vtask delay until. What is the difference between both? The vtask delay until takes two parameters. The first parameter is the reference clock ticks, and the second parameter is how many clock ticks do you want to actually sleep, okay? The delay, you want to have a delay for how many clock ticks, and take care of the units, clock ticks. Therefore, we use a function called ms2ticks, which takes milliseconds and convert it to clock ticks. Therefore, it took 1000 because 1000 milliseconds is equivalent to 1 second, and I want to actually convert 1000 milliseconds, which is 1 second, into clock ticks because this is the delay. I want to print every 1 second. Okay, so vtask delay until takes what? it takes two parameters, while the vtask delay until. However, the vtask delay takes only one parameter, which is how many clock ticks do you want to sleep, or for how long do you want the delay. In clock ticks, the difference is as follows. The vtask delay is not accurate. Okay, the vtask delay until is a more accurate function for creating periodic delays. Why? Because in the vtask delay, when I specify the number of clock ticks I want to sleep, it will start counting from the call of the vtask delay. So actually, I'm here, when I call vtask delay, it will start counting what? It will start counting 1 second. However, in the vtask delay until, it will start counting from what? It will start counting from the reference clock tick, meaning that, let's have an example. Okay, at last wake time, I actually took a timestamp. Let's assume we were at clock tick equal 4. Okay, let's assume when I took my timestamp, I was at clock tick 4. However, when I was executing vtask delay until, I was at clock tick equal 6. So actually, it took me 2 clock ticks to move on from the reference or the timestamp to executing vtask delay until, which means the while and the two prints took, for example, 2 clock ticks to get executed. The vtask delay until will actually create a delay of 1 second. Let's have another assumption that the 1 second, for example, let's have it here, that 1 second is equal, for example, to what? To 5 clock ticks. It is just an assumption. It is not for real. Okay? It is assumption from me for the example purposes. So let's assume that the 1 second is equivalent to 5 clock ticks. So from here, the vtask delay until, I want to what? I want to count 1 second. Using vtask delay until, I'm going to count 1 second, which are 5 clock ticks, from the reference value, which is what? Which is 4. However, in the vtask delay, I'm going to actually start counting 5 ticks from the moment I called vtask delay, which is clock tick 6. So take care, it's really important. The main difference between vtask delay until and vtask delay, that normally if I was executing vtask delay and I want to create a 1 second delay, which is, for example, equivalent to 5 clock ticks, and currently when I was executing vtask delay, I was at clock tick number 6, I'm going to start counting 5 clock ticks from 6. So I should actually return what? Or when at clock tick 11. 6 plus 5 is equal to 11. Therefore, I should return at clock tick 11. If I used this one, I should have returned equal clock tick 11. Okay. However, if I use vtask delay until, I'm going to count my 5 clock ticks from the reference. And the reference is here what? Clock tick 4. Therefore, 5 plus 4 is equal to what? Is equal to 9. So actually, I should return equal clock tick 9. And I was currently at clock tick 6. So I will only sleep for how many clock ticks? I will only sleep for 3 clock ticks, because actually, if I do the calculation, my reference clock tick is 4, and I want to actually sleep for 5 clock ticks. So I should wake up at clock tick number 9. However, when I was executing vtask delay until, I was in clock tick number 6. So should I actually sleep for 5 clock ticks? No, I should only sleep for 3 clock ticks, because to reach 9, I need to what? To sleep for I need to sleep for 3 clock ticks. However, in the vtask delay, I will start counting 5 clock ticks from the call, the moment I called vtask delay, which is at clock tick 6. So 6 plus 5 is 11. And this will not actually create periodic tasks, because I want to actually print hello world and then what? Sleep for 5 seconds. I want to sleep from the moment I called the task that prints hello world. I do not want to sleep from the moment I called the delay. Okay, it does not make sense. Therefore, vtask delay until is used to create periodic tasks. It is more accurate and precise. because it actually takes a reference value, the reference clock tick, which here was the last wake time, and from this reference it calculates what, how many clock ticks are remaining to actually achieve the delay I want. Because it calculates in the future I should return, for example, at clock tick number 9, and currently I'm at clock tick number 6, so I only need to sleep 3 ticks, not the entire 5, because 2 of the 5 were wasted what, in the printing, and I'm here creating a periodic task that should wake up every 5 seconds. Okay, so once it woke up at a certain clock tick, I need to count 5 seconds from this particular moment, not from the moment it starts to call the delay. Okay, we'll have a second example and we'll see also if you did not understand exactly from this example. We created the first task that prints the first hello from task 1. Then we'll create a second task. We gave it the name vtask2. And by the way, we are just creating the functions and methods. Okay, we did not actually initialize the task. We did not use xtask create yet. We did not call xtask create. We are just creating the general functions and methods. And later on, when we call xtask create, this will be actually considered as real tasks. So here we have the task 2, and as an input to it, we have the void asterisk PV parameters. It is the normal definition of any function or method in free RTOS. Then we created an array of chars to represent a string in C called PC task name, and we actually saved in it or stored in it task2 as a string. Then we performed the same concept of having a variable of type tick type, and then we tried to get the current timestamp in clock ticks for the vtask delay until function to create periodic or accurate and precise periodic tasks. So here the last wake time equal task get tick count to actually get the current timestamp or the current clock ticks I am in. Then we have the while one, which is the normal infinite loop we have in any real-time system. We are printing 2 statements, hello from, and then we are printing the PC task name, which will here represent task 2. And finally, we are using what, vtask delay until, giving it the 2 parameters. The first parameter is the reference clock tick I want to start counting from, and the second parameter is how many clock ticks I want to count or I want to sleep. So actually I want 1000 milliseconds, which is equivalent to our 1 seconds. However, it takes it as clock ticks. So we use the ms to ticks function or helper function to convert 1000 milliseconds into clock ticks. And we do not know how many actually clock ticks. The 1 second equal 5 clock ticks was just an example from me. And as you can see, once we use the vtask delay until, it will start counting from what? From this statement, from line 31. Okay, it will not actually start counting the delay from line 35. No, it will start from the reference value, which was retrieved in line 31 using the last wake time variable. Now we have our 2 tasks. We'll move on to our main function or our main method, which here is called main_blinky due to the template you are using for Visual Studio. However, when you do this for Arduino, it will be different, and I will tell you how it is different. Here we created 2 tasks. First, we created them with matching priorities. As I told you, this is now a real life example of how to initialize the parameters of the xtask create function. The first parameter was what? The function name. So we have vtask1 and vtask2. These are these names. The vtask2 and the vtask1, the names I gave to the actually implemented tasks, or the names I used for the actually implemented functions, vtask1 and vtask2. However, the second parameter is just a human name. You want to differentiate between the 2 tasks. So actually, for example, here I wrote task1 and task2. Okay, so it's a human name that is actually not present anywhere in the code. So you can write anything. Then the third parameter is the stack depth. So we allocated 1000 words for each task, the first task and the second task. The fourth parameter is the parameters parameter. If actually it was a function that takes as an input parameter some values and performs operation on them. However, we are not taking any input values for both functions. Therefore, we can have it as null. Then we have the fifth parameter, which is the priority parameter, and we gave both matching priorities of 1 and 1. I could give them 2 and 2, I could have 3 or 3, whatever. But the question asked for matching priorities, so both tasks should have the same number as a priority, whatever this number is. And finally, the handler or the handle, we set it to null because we are not using a handle now. We do not need to actually reference these tasks. Okay, the handle is used when a task wants to communicate with another task. So actually, I need some sort of a variable or a handle to actually point or address this particular task with. Okay, so actually have both tasks. However, if I was going to set them to non-matching priorities, as you can see, I was going to change this one, to example, to 2. Or actually, I could leave this one and I set this 3. It does not matter. Non-matching priorities means a task will have a higher priority than the other task. Finally, we have something that we need to write, which is the vStart or the vTask start scheduler. Once this is called, the scheduler will start working. Okay, so actually, if this is not called, the task start scheduler is not called, the tasks will not operate. Okay, so in order for the scheduler to start working, I need to call the task start scheduler. In Arduino, it is automatically called when you use FreeRTOS on Arduino. As you will see in your project, it is automatically called. You do not need to write it. However, in the Windows simulation, using Visual Studio, you need to write it. It is not actually called automatically. You need to write it. And by the way, once you call the vTask start scheduler, a new task will automatically be created called the idle task. Remember, as I told you before, we cannot have 0 tasks in the running state. At least I must have 1 task in the running state. So what will happen if actually all of the tasks in my system are in the waiting state? They are blocked or waiting for an IO device to use, or they are just having some sort of events like delays, and actually they are waiting to be woken up after the delay finishes. I must have at least 1 task in the running state. But however, I do not have any tasks that can be selected to run in the running state. So the FreeRTOS system actually creates automatically a task called the idle task, and this task is given priority 0, which is the lowest priority. Therefore, priority 0 is actually used automatically by a task that is created by our scheduler called the idle task. When no other task is being run in the running state or no other task is being executed, the scheduler automatically will choose what? The ideal task, because it has the lower priority or the lowest priority, which is 0. Therefore, if I want to create multiple tasks and I want to set one of them to the lowest priority, it is better to make it 1, not 0. Because actually, if it has 0, then you will be actually facing a problem selecting between the ideal task and this task, so your program will not work correctly because the idle task does not have any code inside it. It's an empty task. Yes, you can overwrite it, but we will not tackle how you can overwrite the idle task. So it is actually, as a convention, the lowest priority task. As a programmer, it is better to give it priority 1, not 0, because 0 is used for what? Is used for the idle task. And yes, you can actually assign the same priority for multiple tasks, but I mean, giving it priority 1 as the lowest priority will prevent it from clashing with the ideal task with priority 0, because if a task has priority 0 and the ideal task automatically created has priority 0, the scheduler now needs to choose between one of these tasks, 2 tasks, and then it will perform time slicing. So it will actually, our program or our system will not work perfectly. Okay, so actually the task start scheduler will automatically create an idle task with priority 0 that will run if no other tasks are in the running state, or all of my tasks are blocked. So I need to have at least 1 task in the running state, and the idle task will be in the running state. And take care, the idle task is created when I call the vTask start scheduler. It is not present beforehand or before. It will actually be created once I called this specific function or method. So now we want to trace the execution of this code, once with the matching priorities and the other time with the non-matching priorities. So let's start with the matching priorities. And as you can see, both tasks are given priority 1. So time slicing will occur. However, these are not continuous tasks. These are periodic tasks. The difference between a continuous task and a periodic task is that a continuous task does not have any delay inside it. However, a periodic task has some delay because it will what? It will sleep and wake at fixed intervals using the vtask delay until, as I showed you earlier. So the question that will be asked to the scheduler, which task will run first, task 1 or task 2? The answer is that the scheduler will choose randomly one of these two tasks to actually run first, because both have the same priority, because both have matching priorities. The scheduler could not actually prefer one task over the other, therefore it will choose randomly one of these two tasks to run. Some people say it will choose actually the first called task, which is task 1. However, this is not a rule of thumb, and this is not always the case. It may choose task 2 to run first before task 1. So here, let's just trace the execution. Let's assume that task 2 was chosen before task 1. Both have same priorities, so the scheduler could not actually choose one of both tasks to run first. So randomly, it picked task 2. So task 2 will execute. Okay, task 2 will execute first. It will print hello from task 2, and then will go into a sleep state. So it will be moved from the running state to the waiting state. Initially, it was in the ready. The scheduler chose it, so it moved to the running state. Then it was going to sleep, so it's an event. It will go to the waiting state. Once it went to the waiting state, the scheduler chose the second highest priority task. And currently, the scheduler has two tasks in the ready state, task 1 and the ideal task. And do not forget about the ideal task. So it will choose task 1 because task 1 had priority 1, while the ideal task has priority 0. So it chose task 1. Now task 1 printed hello from task 1 and then went to the waiting state because it has vtask delay until. Both tasks are what? In the waiting state. So which task will run? The ideal task. And here we will be having the ideal task. The ideal task will run for a specific period of time until task 2 finishes its delay and wakes up and moves back from the waiting state, or goes from the waiting state to the ready state. Therefore, the scheduler will see, oops, we now have what? A task with a higher priority, which is task 2. So what? Task 2 will run. Okay, and then when task 2 finishes running, in the middle, task 1 was actually finished waiting. It is in the ready state. However, task 2 had a higher priority than task 1. So actually, task 2 will continue printing. When task 2 moves to the waiting state, task 1 is now actually in the ready state. So it will be selected. So task 1 will run. And when task 1 prints hello from task 1, it will be in the waiting state with task 2. So which task will run? The ideal state. Actually, could have the different option of starting with task 1 to idle, task 1 to idle. But however, our scheduler chose randomly that task 2 will start executing because we have what? Matching priorities. Task 1 and 2 had priority 1, same priority. However, the idle task had priority 0. So we eliminated the idle task from our choice at the beginning, and the scheduler chose what? The scheduler chose task 2 instead of task 1. It could have chosen task 1. No one knows because they have matching priorities. Okay, so what will happen if we had non-matching priorities? If we go to our code, here task 1 was given priority 2 and task 2 was given priority 1. So automatically the scheduler will know for sure that it should execute task 1 before executing task 2. Because what? Task 1 has a higher priority. Now with the non-matching priorities, task 1 has priority 2. Therefore, it will always be the first task executing. However, in the matching priorities, you could run your program. You'll find task 2 running first. You may find then later task 1 running first because they have matching priorities. However, in the non-matching priorities, the larger the number, the higher the priority. Therefore, task 1 had the higher the priority because it had the bigger number, which is 2. So actually, if we were going to trace it, it will be like this: task 1, task 2, then idle, then task 1, task 2, then idle. Because what? Task 1 has the higher priority, which is priority 2, so it executed, printed hello from task 1, then went to the waiting state due to the vtask delay until, or the delay we created. We will check the ready states. We have the idle task and task 2. Task 2 has a higher priority than the idle task because task 2 has priority 1 and the idle task has priority 0. So the scheduler will choose task 2. It will move to the running state. It will print hello from task 2. Then it will go into a delay and will move to the waiting state. Both task 1 and task 2 are in the waiting state, so the idle task will be running in the running state. However, task 1 finished its waiting period, it returned back to the ready state. The scheduler will preempt the idle task and task 1 will actually start executing. At this time, task 2 returned from the waiting state to the ready state. However, task 1 had a higher priority than task 2, so it will actually execute, and once it reaches its delay part and moves to the waiting state, task 2 will be selected or elected to be in the running state, and so on. Okay, so here the difference was which task will start, since we are having both periodic tasks. However, the lecture has some examples about continuous tasks, so it is really important to actually take care or take a look at the lecture example, because it had a continuous and a periodic task running together, or in the same program, I mean. Now, if we actually want to trace this on a graph, and it is a common question in the exam to trace this on a graph. So here, trace the execution of your code on a piece of paper showing the idle task. Here, I will show you both examples of using vtask delay until and vtask delay to actually highlight the main problem we have with vtask delay. If we are going with vtask delay until, and by the way, the matching and non-matching priorities will have the same figure or the same graph. It will just depend which task started first. However, the rest of the sequence will be the same because it is, I repeat, it is a periodic task, or they are periodic tasks. So using vtask delay until, let's assume that here actually we used the matching, non-matching priorities, I mean, and task 1 has the higher priority, so it will be the first task to execute or to run or to move to the running state. So actually, this is task 1, and it started here and it finished here. So at this point, it called what? At this end, it called the vtask delay until. However, the vtask delay until will actually count from where? From the reference tick count, which we actually took from the last wake up time variable. As I know, actually there was some code before this, so actually this could have taken some time. However, we just ignore this time. Nevertheless, do not care about what I said, but some people will tell me there was 2 lines before I actually took the reference. This will only be executed the very first time, because later on we are stuck in the infinite loop. So it is a negligible error that we do not care about. However, let's continue. I started task 1. This is the period of task 1. Actually, at the end, it called vtask delay until. So vtask delay until will count 1 second from the reference parameter it was provided with. So actually, it will count 1 second from where? From the start. If we go back to Visual Studio, the last wake time is the variable that is containing the reference. So it's here, for example, it will count from clock tick number 4. It will not count from clock tick number 5. If we assume this is 4 and this is 5 and this is 6, I mean, it will start counting from clock tick number 4, not from clock tick number 6. Therefore, the 1 second is what? It starts from here and it will end here. However, once task 1 moved to the waiting state, what will happen? Task 2 will run because it has the second highest priority, which is priority 1. So it will run. It will run for how many long? It will run for a period of time. And here it will finish. Here we will call the vtask delay until. And similar as task 1, the vtask delay until takes what? The reference time provided with it or provided to it. So it will actually count 1 second from the beginning of the task, not from the moment I called the delay function. That's vtask delay until. However, here we have the idle task, and the time of the idle task is actually
we know that task 1 will have what? Will have a 1 second delay. So actually the idle task will be running for how many clock ticks? Will be running for 1 clock tick minus the time T2 took minus the time T1 took. So actually this will be the remaining time. Task 1 executed for T1. Task 2 executed for T2. I want to know how many clock ticks will the idle task execute in or execute for. How long? Okay. So actually I know that at the beginning from this point to this point it is 1 second. As you can see, the idle task is within the phase or the period of 1 second. So 1 minus the time taken by T2 and the time taken by T1. I'm going to subtract this 1 sec. I'm going to subtract the time taken by task 1 and the time taken by task 2 from the 1 second period. Therefore, it will result from what? It will result for the time the idle task spent running. Okay? Because here task 1 will what? Will return from the waiting state to the ready state, and the scheduler will select it to run. And as you can see here, the 1 second here will finish. So actually when task 1 finishes executing and moves to the waiting state, task 2 will be ready, it will be in the ready state because it finished its 1 second. Therefore, the scheduler will select task 2 and it will run, and this sequence will be repeated, so on. So the most important parts are as follows. The task 1 using vtask delay until, it will count 1 second from the beginning of the task, not from the end. Therefore, this time is 1 second. Task 2 will actually also count 1 second from the beginning of its execution, not from the moment I called vtask delay until. And the idle task will be what? The idle task lies between the 1 second of task 1. Therefore, the time spent by the idle task is 1 minus the time taken by task 1 plus the time taken by task 2, which is 1 minus T2 minus T1. Okay? Because actually the idle task will only work until a higher priority task is in the ready state that will preempt or kick this task, the idle task, from running. If we go into vtask delay, not vtask delay until, and you can see now the difference is that if I start with task 1, I'm going to calculate the 1 second from the moment I called vtask delay, not from the moment I started executing task 1. So as you can see here, the 1 second will start from here. From the moment I called vtask delay. So actually here, task 1 finished and it went to the waiting state. Task 2 has the second highest priority, so it will start executing, and here it will finish and it will start counting the 1 second from the moment it finished. This is when you use vtask delay and not vtask delay until. It's really important. Then the idle task will run for this period of time. As you can see, the idle task is actually running in the 1 second from here to here. So this period lies in the 1 second period from here to here. So it will be 1 minus what? The execution of T2, because this 1 second period resembles or actually represents T2 plus the time taken by the idle task. So to know the time taken by the idle task, it will be 1 minus the time taken by task 2. Because I started counting 1 second from the end of what? Of task 1. And the end of task 1 marks the beginning of task 2. So the time taken by task 2 plus the the time spent by the idle task will actually be equal to 1 second. Because actually the idle task will be running for the rest of the time until task 1 returns back to the ready state. So you can see here the difference, that we started at the vtask delay until counting from the beginning of task 1. However, in the vtask delay, we started counting from the end of task 1, from the moment we called vtask delay. Therefore, it is better to use what? Vtask delay until to create periodic tasks. And do not use vtask delay unless stated in the exam. You need to actually use vtask delay and trace it. Otherwise, we use vtask delay until. Now let's move on to the next question. What does the code in the below figure do? and modify it so that the 3 tasks get to print out a message. The 3 tasks should be continuous. So actually, and here trace the execution of the below figure and the execution of your modified code on a piece of paper. So we have this code. This is the original code that it wants me to trace and see what it is performing. We have here how many tasks? We have 3 tasks. Task 1, task 2, and task 3. Okay? And as you can see, these 3 are continuous tasks. They are not periodic. I do not see a vtask delay until or even the vtask delay in its body. Okay? So actually, there are no delays. It means they are continuous tasks. Here, task 1, it is printing task 1 is running. Task 2 is printing task 2 is running, and task 3 is printing task 3 is running. However, I do not know the order of execution. I need to actually check their priorities and their initialization using xTaskCreate. So as you can see here, all 3 are tasks are actually initialized using xTaskCreate. We have here the function name vtask1, vtask2, and vtask3, the actual name implemented in the code. Then the human name, we wrote task 1, 2, and 3. It is just a human name for you while you are debugging. Then all of them are given the same stack depth, which is 1000 words. They cannot actually operate outside of these 1000 words. Then we have here their parameters set to null, so they are not taking any input parameters. They are like void functions. However, you need to actually in the signature say void asterisk PV parameters. It is in the definition of the function. However, it may actually take null as a parameter, or it may take no parameters at all. But you need to specify it when you are creating a task, or when you are creating the function that will later on be a task. Then I will have here the priorities, and they are given non-matching priorities. As you can see, we have priority 3 to task 1, priority 2 to task 2, and priority 1 to task 3. And finally, their handle is set to null, meaning that I do not want to access them, or I do not want a task to actually point or access another task. And at the end, we have the vtask start scheduler. Once it is called, a force task will be actually automatically implemented or created, which is the ideal task with priority 0. So yes, initially before the vtask start scheduler, we had 3 tasks. After calling the vtask start scheduler, we'll be having 4 tasks with the newly implemented or the newly created ideal task with priority 0. Therefore, it will have the lowest priority ever compared to the other 3 tasks. As you can see here, as a programmer in semester 7, and after I describe this tutorial to you, what will be the order of execution of these tasks? It is simple. As you can see, task 1 is given the highest priority, which is 3. So task 1 will always run. However, task 2 and 3 will not run because task 1 is a continuous task. So it will always run. It does not have any delay. It will not move to the waiting state. It is not actually waiting for any IO device. It will not be blocked by such IO device, Therefore, task 1 will always execute because it has the highest priority, which is priority 3. I repeat, task 1 will always execute because it has the highest priority, which is priority 3. And since it's a continuous task, not a periodic task, task 2 and task 3 will not even be executed once. Okay, they will never be executed. So I would be having something like this. Task 1 is running. So if I go here, I'll be having something like this. Task 1 is running, then task 1 is running, then task 1 is running, and so on. Because task 1 is continuous, it has the highest priority, nothing will actually prevent or preempt this task, so it will always run forever, and the other 2 tasks will never run. And this is actually the problem stated in the question. Modify it so that the 3 tasks get to print out a message. In this code, the given or the original code, task 1 will only be the task printing, will only be the only task that is printing a message. However, the question wants us to modify our code so that all 3 tasks will print a message. And here comes the priority manipulation. And by the way, it is very dangerous to manipulate priorities. However, we will tell you how to manipulate priorities. Because if you do or perform a simple mistake or a simple calculation mistake, your system may crash. Okay, this is priority manipulation. So a task, we will introduce the concept of tasks changing the priority depending on the priorities of other tasks, and we'll see how to perform this. But as I stated, it is very dangerous, but we'll teach you how to do so. So if we go to Visual Studio, and by the way, it will not work on Mac. I mean, yes, there is Visual Studio for Mac. However, the free RTOS is not currently working because it uses a Windows port layer, not a Mac OS port layer. However, if I find a solution, until then, I'm just writing some codes. However, it will be executed on Windows machines, not Mac machines. If I find a solution, I will post it to you on the CMS, MET, and Piazza platforms. So we have this code, okay? And actually, as I stated in the previous question, I will not write from scratch because you took this on campus. So this should be just a quick revision. So I will be commenting on the solution, not writing the solution from scratch. So as you can see here at the beginning, 2 new lines were added. And these two new lines were what? Task handle and task handle. So I'm creating 2 task handles. And as if you recall, the task handle is the 6th parameter in the task create function. So here I'm definitely creating a task handle variable, so I can what? I can put it as the 6th parameter in the task create function code. So here I'm having task handle, task2 handle equal null, and task handle, task3 handle equal null. So initially they are actually set to null. However, instead of actually putting null directly to the task create 6 parameter, I put null inside a variable, and this variable is of type task handle. It's a special type implemented in FreeRTOS. And when you call the task create, what will happen? It will assign an instance from this task into this variable. So initially this variable will be null. However, when the task create is called on this variable, an instance of the task will be added or initialized inside this variable. So as you can see here, task 1, we did not provide a handle because it has the highest priority, and we'll see why we did not provide it a handle. However, task 2, the 6th parameter was changed into x task 2 handle, and task 3, its 6th parameter was changed into x task 3 handle. And as you can see, this is the variable, but here we are passing the address. You can see that we added an AND symbol. This means it is the address. Okay, just write it as it is. Okay, we will not go into deep. Why are we passing an address and so on? Just know that we are passing an address. So AND x task 2 handle and x task 3 handle. So actually we provided a 6 parameter for task 2 and task 3 while calling the x task create function or method. Okay, so now task 2 has a handle and task 3 has a handle. The role of the handle is actually to point to this task. If another task wants to retrieve or communicate with a different task, it communicates through this interface, which is this handle. Okay, so let's see the next changes. Here we have task 1. Task 1, at the beginning, we have a variable called priority or UX priority. And actually, I'm trying to get the priority of this task. So as you can see, UX priority is equal what? Task priority get of null. And of null means get me the priority of myself. So when I actually provide the task priority get with an input parameter null, it means retrieve the priority of this particular task that I am executing. Okay? So actually here I'm trying to retrieve the priority of task 1, which is the task that is executing. And since it has the highest priority, which is priority 3, and the question prevented us from creating periodic tasks. It stated in the question that we need each of the 3 tasks to print a message without affecting their continuity. So they must be continuous. Okay, here while 1, I'm printing task 1 is running. However, I'm here using a function called task priority set. And task priority set takes 2 input parameters. The first parameter is the handle of the task that you want to set its priority or you want to modify its priority, and the second parameter is the priority you want to modify or set. That's why we created a handle for task 2 and task 3. As you can see in task 1 here, we are trying to modify the priority of task 2 by setting it to the priority of task 1 plus 1. Therefore, let's trace. If I get the priority of task 1, which is 3, now I'm setting the priority of task 2 to what? To 3 plus 1, which is what? Which is 4. Therefore, task 2 will have a new priority, and this is a dynamic change of priority, and therefore it will be of priority 4, which is higher than 3. The scheduler will notice and will preempt task 1, and which task will run now? Task 2, because we dynamically changed its priority from 2 to 4 by actually doing priority plus 1. Priority variable contains the priority of task 1, which is 3 plus 1, therefore it will be 4. Now I'm changing the priority by using the task priority set of task 2. I'm changing it to 4. Now we'll go and execute what? Task 2. Task 2 will perform the same functionality. First of all, we'll be having a parameter called UX priority, and this parameter will save or will store the priority of this particular function. So UX task priority get of null means get the priority of the task I am executing, which is task 2. Currently, task 2 priority is what? Is 4. Therefore, it will retrieve it, and the UX priority variable will contain 4. Now, in the infinite loop, I'm going to print task 2 is running. Then I'm going to set the priority of 2 tasks. The first one, I'm going to set the priority of what? Of task 3 in 2. My priority plus 1. So 4 plus 1 is 5. So now I'm changing the priority of task 3 from 1 to 5. And then I'm setting the priority of myself 4 minus 3. And therefore, I'm setting my priority to what? To 1. So again, here I'm setting the priority of task 3 into 4 plus 1, which is 5. Therefore, it will have, or it will have the highest priority. And the second thing, I'm setting the priority of myself. Therefore, I used null, which means, or which donates the priority of myself as task 2. I'm setting it to 4, which is my priority, minus 3. Therefore, it is 1. It will now have the lowest priority. And now the scheduler will take notice that task 3 now has the highest priority, which is priority 5. So it will select task 3 to what? To run. So task 3 will run. At the beginning, we have the UX priority variable, which is being used to actually retrieve the current priority of task 3 using the task priority get. So task priority get takes null as an input, which means retrieves the priority of myself as task 3, which is currently 5. And therefore, I'm going here to print task 3 is running, and followed by the vtask priority set. I'm now trying to set my own priority as task 3. Therefore, I used null, and I'm trying to set it to what? To my priority, which is 5 minus 4, which will result in what? Which will result in priority 1. Therefore, now I have 2 matching priorities. Task 2 and task 3 share the same priority, which is 1. However, task 1 has a priority of 3. Therefore, the scheduler will take notice and will be notified and will preempt or will kick task 3 from executing and will select task 1 to run. And after selecting task 1 to run, it will have what? Because it has the highest priority. It has priority 3. However, task 2 and task 3 both have priority 1. So task 1 was selected. Task 1 will perform the same cycle again. Task 1 will actually retrieve its own priority, which is 3, and then will print task 1 is running. And afterwards, it will what? It will change the priority of task 2 from 1, this time into what? Into 4, because my current priority, which is of task 1, is 3. 3 plus 1 is 4. So I'm going to change the priority of task 2 from 1 to what? To 4, making it the highest priority task, which will be selected by the scheduler. And so on. So even if task 2 and 3 had at a particular moment the same priority, but task 1 had the highest priority, which is 3, so actually the scheduler will always select task 1 and task 1 will be the task running, and it is only modifying the priority of task 2. So when I actually access task 1, it will change the priority of task 2, making it the highest priority task. And when we move to task 2, we'll be seeing that task 2 modifies the priority of task 3, making task 3 the highest priority, and then it decreases its own priority, making it the lowest priority, and so on. So if we actually trace this, we'll be having task 1 running, then task 2 running, then task 3, then task 1, then task 2, then task 3. And these are continuous tasks, therefore the idle task will never execute because they are continuous. They are not periodic, they do not go to a waiting state, or they do not go to the waiting state. Therefore, task 1 automatically runs. After it finishes running, it will modify the priority of task 2 at the same instance, making it the next highest priority task, or the current highest priority, because task 2 will have a priority of 4 compared to the priority of 3 of task 1, and so on. So if we want to trace this as actually graphs, at the beginning, the original code, as I told you, it will continue executing forever. So before modifying the code and using the task handle, we had 3 continuous tasks, 3 different priorities. However, since they are continuous, the task with the highest priorities will always run. It will run forever. And here, task 1 ran forever. However, the ideal task, task 2 and task 3 never ran. However, after we modify our code, we'll find out what? That task 1 will run for some specific time, or for a period of time. And then here, when task 1 modifies the priority of task 2, making it higher than its own priority, task 2 will run. Then at the end of task 2, it will modify its own priority, making it the lowest priority, and it will modify what? The priority of task 3, making it the highest priority. Therefore, task 3 will be the highest priority task, and it will execute. After task 3 finishes executing here at this specific time, it will decrease its own priority, making it the least priority, which is the same priority as task 2, which was 1. However, task 1 had the highest priority, which is 3. So the scheduler will select task 1, and we will repeat the same cycle. And as you can see here, the idle task did not run at all actually. Because we are having here continuous tasks, we do not have any delays, so we do not go to the waiting state, and the continuous tasks are always altering the priorities of each other. And this is the use of the 6th parameter of the xTask create, which is the handle, to actually, if I want a task to retrieve or set the priority of another task, it can use this handle. But it is very dangerous, as I told you before. Finally, the detailed solution of this practice assignment can be found on the CMS and MET websites, titled Practice Assignment 5 Solution. Now we are done with this tutorial. If you have any questions, don't hesitate to post it on Piazza or send us an email. I hope you guys enjoyed this tutorial, and see you next time.